Hello chemistry students, this is Mr. Anksman and this is your section 3.2 notes, which is on units of measurement. As we're going through the notes, make sure you're recording anything that's typed in blue. So starting with SI units. So what makes metric units easy to use? So all metric units are based on multiples of 10. As a result, you can convert between units easily. All we have to do is move the decimal point. So there are 7 SI base units. You see they're listed over here on the right. The meter, kilogram, Kelvin, second, mole, candela, and ampere. So every other unit of measurement is considered a derived unit. So I'll start with units of length. In the metric system, the basic unit of length is the meter, and we use just a lowercase m to represent meter. Then we want to know the metric prefixes in order, and they're listed in order from big to small. So we got kilo, hecto, deca, then the base unit, which could be any of those metric units that we use, gram, meter, liter, joules, calories, etc. And then deci, centi, milli. So we put the prefix in front of the name. We use, for example, a capital D for deca. And then grams would be the unit of measurement, so this would be decagrams. Now, along with those that were already listed, you also want to know some of these, as in mega, which is 1,000,000 times larger than the unit it precedes, or 10 to the 6th. And then kilo, deci, centi, milli, those were all listed on the previous slide. But then you also want to know micro, nano, and pico. So micro is 1,000,000th, nano is 1,000,000,000th, and pico is 1,000,000,000,000th of the unit it precedes. So those aren't used very often, but you still want to be aware of those. So for the metric conversions, so it's easy to make metric conversions because all we have to do is move the decimal point. And so you want to record this list up here too, where it goes from large to small in this order. And having this will help us determine which direction and how many places we're going to move the decimal point. So a couple of examples, and you can pause the video and try this out here too. But going from milli to hecto, so we're going milligrams to hectograms. So the decimal point would be here just to the right of 8. So if we look on our chart up here, we're starting with milli and we're going over to hecto. So we're going to go 1, 2, 3, 4, 5 places to the left. So you would take the decimal point and you go 1, 2, 3, 4, 5 places to the left, and you'd fill in zeros in front of those, in front of the 2 for placeholder zeros. For this one on the right, we're going from hectoliters to centiliters. So we're starting here with hecto, and we're ending up right here with centi. So we're going to go 1, 2, 3, 4 places to the right. So you take this decimal point, you go 1, 2, 3, 4. You put a couple of placeholder zeros after the 5, and that's your answer. So that's what we should have right there. 0.00258 hectograms and 874,500 centiliters. Okay, next, units of volume. So for volume, we generally use the liter as our base unit. A liter is defined as 1,000 centimeters cubed. And you also have 1 milliliter and 1 centimeter cubed are the same volume, so you can convert between those two. They're the same thing. 1 milliliter and 1 centimeter cubed are the same thing. And you see some figures that give you an idea of relative size. For all these metric measurements, it's good to have a relative idea of how big or small they are. So 1 liter is like a big bottle of pop or juice or whatever, and then a milliliter would be like a 10 drops or so. So you see some other relationships between units of volume. So a liter is about the same as a quart. A milliliter is about 20 drops of water. A cubic centimeter is the same thing as a milliliter. So it's about the size of like a cube of sugar. And microliter would be a crystal of table salt. All right, for units of mass, we have the kilogram. That's our SI, basic SI unit of mass. We also use the gram a lot. So a gram is 1,000th of a kilogram. So it's also defined as the mass of 1 centimeter cubed of water at 4 degrees Celsius. And these are some units of mass and what you can relate them to. So a kilogram would be like the mass of about a small textbook. A gram would be a dollar bill. A milligram would be 10 grains of salt. And a microgram would be a particle of baking powder. Okay, then we have weight. Weight is a force that measures the pull on a given mass by gravity. So if gravity changes, as in you go to a higher elevation or you go out into space, the mass doesn't change, but your weight does. So an astronaut in orbit is weightless but not massless. Mass stays the same. For units of energy, energy is defined as the capacity to do work or to produce heat. And then the SI unit of energy is the joule. We use a capital J to represent joule. Along with joule, we also use calories. So calorie is a quantity of heat that raises the temperature of 1 gram of pure water by 1 degree Celsius. So here's a couple practice problems. So you're driving 2.65 kilometers per minute in Canada. What is the speed in miles per hour? And would you get a speeding ticket if driving on the freeway in Minnesota? So this is kind of a preview of what you're going to see in section 3.3 with dimensional analysis. So it's a conversion problem. So you want to convert 2.65 kilometers into miles, and you can use this as a conversion factor. And you want to convert minutes into hours. So you know there's 60 minutes in 1 hour. So you want to try to practice making that conversion. For the process for doing this, you'll see it's a dimensional analysis, and we'll practice that really next section. But you can try that one out. And then also convert the 71.45 decagrams into milligrams. So you can pause the video and try those two problems. And there's your answer. So for now, if you didn't use the process of dimensional analysis like this, it's okay. But this is the type of conversion problem you'll be doing in the next section. This is using the bump method, as in bumping the decimal point one direction or the other. So to go from deca to milli, you have to move the decimal point 4 places to the right, and you fill in the 2 placeholder zeros at the end. Okay, now we have temperature scales. So temperature is defined as a measure of how hot or cold an object is. So we're going to use 2 scales. We're going to use degrees Celsius and Kelvin. So we're not going to do anything with Fahrenheit. So you don't have to worry about converting between the Fahrenheit scale and the Celsius scale. So just Celsius and Kelvin is what we're going to work with. So the Celsius scale sets the freezing point of water at 0 degrees Celsius and the boiling point of water at 100 degrees Celsius. On the Kelvin scale, the freezing point of water is 273.15 Kelvin, and the boiling point is 373.15 Kelvin. Now with Kelvin, we just say Kelvin. We don't say degrees Kelvin, okay? So just a minor point right there. So it's just capital K to represent that scale. So this is a comparison between Celsius and Kelvin. Celsius is the one on top, Kelvin on the bottom. Then the 0 point on the Kelvin scale is 0 Kelvin, and that means it's absolute 0, and that's the coldest possible temperature. At absolute 0, all particle motion stops. So that temperature is negative 273.15 on the degrees Celsius scale. Now, one thing you see between Celsius and Kelvin, um, the change in temperature is the same for both. As in, if the temperature goes up 10 degrees Celsius, it also goes up 10 Kelvin. It's just the two temperature scales start at a different point, but they change by the same amount. So the conversion between them is relatively easy. If we know the temperature in degrees Celsius, and you want to record this equation right here, if you know the temperature in degrees Celsius, you just simply add 273 to it to get to Kelvin. Or if you know the Kelvin temperature and you want to get to degrees Celsius, you just subtract 273. So we have normal human body temperature is 37 degrees Celsius. What is this temperature in Kelvin? So again, go ahead and pause the video and you can answer that question. So we take our Celsius temperature and we add 273 to it, and you get 310 Kelvin. So the change of 1 degree on the Celsius scale, that's equivalent to 1 Kelvin on the Kelvin scale. So yes, that is true. Okay, next we have density. And the key question is, what determines the density of a substance? So density is defined as the ratio of mass of an object to its volume. So here's another equation that you want to record. Density equals mass divided by volume. And you want to be able to rearrange this equation and solve for any of those variables. So this figure compares the density of 4 substances: lithium, water, aluminum, and lead. So you have 10 grams of each of these, but because lithium has the smallest density, it's going to have the greatest volume. So 10 grams of lead doesn't occupy much volume because it has such a large density. And also we use density to determine what layers will float on other layers of liquids. Because of differences in density, liquids separate into layers. So we have corn oil over here. Corn oil is going to have the lowest density of those liquids, and corn syrup is going to have the greatest density. Water is going to be somewhere in the middle. So you don't have to record all this down, but what happens to the density of a substance as its temperature increases? So for most things, when the temperature goes up, the volume goes up, so the density will decrease a little bit. One thing you want to know, water is an important exception. Especially when water melts, the density goes up when it goes from a solid to a liquid. There's a density calculation problem. So you want to try this one out. You have a copper penny has a mass of 3.1 grams and a volume of 0.35 centimeters cubed. What is the density of copper? So you want to show your work, and when you write out your answer, you want to pay attention to sig figs, and also make sure you include the units. So go ahead and pause the video and do this calculation. So there's the answer. Density is mass divided by volume. So we end up with 8.9 grams per centimeter cubed. And can you assume that something with a low weight will float in water? So you can think about this answer. And no, it's not the weight, it's about the density that will determine if something will float or sink. So a couple of key concepts just to review. All metric units are based on multiples of 10. As a result, you can convert easily between units just by bumping the decimal point. Scientists commonly use the two equivalent units of temperature, degrees Celsius and Kelvin, and density is an intensive property that depends only on the composition of the substance. There's a couple of key equations. Make sure you have those down. And these are the terms. You want to pause and make sure you get these recorded too. And that's all for section 3.2. Have a